Okay, so we have defined arithmetic circuits. It is a DAG with internal vertices and leaves. So leaves are the formal variables x1 to xn. Then there are the edges are the wires with the constants, and internal vertices are gates. They can add or multiply polynomials. So we will say that an arithmetic circuit solves a problem or computes a polynomial in the following sense. So we defined that in terms of family of polynomials and family of circuits, right? So given a family of polynomials and given a family of circuits, we will say that those polynomials are being computed by the circuits if Ci is equal to Fi, right? So this is the meaning of solving a problem, right? We basically mean that an infinite family of circuits is computing an infinite family of polynomials. Okay, so in this sense now we can talk about the resources. So in this case we can say that the set of polynomials f can be solved by not well, it can be solved in size bounded by size of Cn. Okay, so for n variate polynomials in your family, n variate polynomial in your family f, that's a single one, that can be computed by a circuit of size Cn, size of the circuit Cn. So that's an upper bound on the size complexity, and depth bounded by the depth of Cn. Okay, so size of Cn you should see it as a function of n, and depth of Cn also you should see as a function of n, and these two functions basically tell you the circuit complexity of the set of polynomials f. To compare with Turing machines, very vaguely speaking, depth can be seen as or can be thought of as. So what do you think is depth in terms of time or space? Is it time or is it space? Well, obviously it is time, right? Because if you think of a set of microprocessors, each being a gate, addition or multiplication gate, then the time taken to compute a value of the polynomial is basically the maximum length of gates which you have to traverse. So depth can be thought of as time in parallel. In parallel algorithms. And size can be thought of as size is the corresponds to the other parameter, which is space in parallel algorithms. Well, I mean, if you try to implement a circuit on a Turing machine, then size of the circuit will basically will give you the space complexity of the Turing machine. Okay, so vaguely speaking, you can think of depth versus size as time versus space. Okay, but formally we have defined these things, so we'll just work.
Maximum number of gates in one layer, I mean overall layers.
No, space will be the overall size of the circuit. If you implement this circuit in the Turing machine, in the Turing machine model, then the bigger the size is, the more will be space requirement, because all that all those gates you have to actually take care of them in the tape.
For circuits, like variables may be reused somewhere in later layer, but for formulas, like once it is used, we can reuse that space. For example, input layer, if we read the variables once, we don't need that space anymore.
I'm not sure whether you can reuse at the level of the cells in the tape. But so, anyways, for circuits it is this. For special models we have to think. Yeah. So yeah, all this gives us. So this gives us a new way to measure the complexity of problems. And problems now would mean polynomials. Right? So now we can systematically measure the complexity of polynomials, and these are our new problems. So the study of this is called arithmetic circuit complexity. Okay, so arithmetic circuit complexity theory or algebraic complexity theory is the study of polynomials with respect to the size and basically size of arithmetic circuits that can compute them. Okay, so arithmetic complexity classes. So based on so once you have these measures formally defined, you can now talk about complexity classes. So now you can characterize many problems in the same class depending on how easy or how hard they are in the arithmetic circuit model. So such classes were first defined by Valiant. So arithmetic complexity classes were first defined by Valiant around in the 70s. What will be the most interesting complexity class that you would want to define? So just like P is the most interesting complexity class in the Boolean world, here the most interesting complexity class will be an analog of polynomial time. And once you have defined that, then the next important thing would be, or interesting thing would be, analog of NP. So those were formalized by Valiant. So in particular, the arithmetic analogs of P and NP. Okay, but we have to do it in an algebraic or in this arithmetic sense. So let us do that. So the arithmetic version of P is called VP. Okay, V stands for Valiant. So this is Valiant's P. So how do you want to define VP? So in P we said polynomial time, right? Here we should we say polynomial depth? No, so a better thing would be to say polynomial size, right? So we will define VP, or Valiant define VP in terms of families of polynomials. So VP consists of polynomial families say Fn, right? So every element of Vp is actually an infinite sequence. It is this sequence of Fn's. Fn is a n-variate polynomial, and so this, for this polynomial family, the property that you want is that can be solved or computed by circuits, arithmetic circuits of size. So what do you want the size to be bounded by? Poly in n, right? N is the only parameter here. So by size poly n, so poly n is just n to some absolute constant over all the constants, right? Every constant is allowed. So it could be n or n square or n cube or n to the 1000 or n to the 1 million, right? All these are shoved together into this class. So is this enough? No, variables are, it's a parameter. So whatever Fn you are looking at in this family, for that Fn the size should be poly n. Yeah, so there is an additional thing, so which may not be very intuitive at this point. So you want the degree also, or Vaillant wanted the degree to be not too high. Okay, so the size polynomial n is still understandable, but why is this condition on the degree also needed? Sorry?
Otherwise, 2 to the power n
Yeah, so
evaluating at some point with some high degree, exponential degree.
right, so
real time.
exactly, so why the degree condition? So this needs some explanation, and this is basically what was already suggested, that you want, so once you have a circuit which is small, small means poly n, you also want it to be practically implementable, right? So practical implementation means that every aspect of the computation you would ideally want to be efficiently implementable on a Turing machine or on a normal computer. So one necessary condition for that is the degree should not blow up too much, because in size n you have seen in the last class the degree could grow up to more than 2 raised to n. Now if n was 100, then this basically means that the degree could become 2 raised to 100, right? So that kind of conflicts with time and space, poly time and space. So a good way to control that is to control the degree. Okay, so degree is restricted to poly n. So now in every gate in your circuit for polynomials in VP, first of all there are few gates, so poly n many gates. Moreover, at every gate a polynomial of degree only poly n is being computed. So when you want to evaluate your circuit at a point, let's say point x equal to 2, then in no intermediate node could you get 2 raised to 2 raised to n in the evaluation. Okay, so the number computation will be small. So we don't want the circuit at a point to become too large. Say over rationals. But this still is not enough for efficiency, because we are not saying anything about what kind of constants are used on the wires. So constant on the wires could themselves be too large, right? Um, but that I think is fair, because if your circuit already has constants which are too big, then obviously if you try to evaluate it at a point, values could also be too big. Okay, so that is not a implementable circuit. But as long as the constants are small, the circuit evaluation at small points, this is what the definition of VP current is. So this is something external to our model, to our algebraic model. This degree condition is external, but this is how VP is defined. Any questions?
So if you wanted efficient implementation, you said in the earlier class that sometimes you do include constant sizes.
Right.
Size of the circuit.
Yeah.
Why wasn't that included in this definition itself, in the size collier?
Right. So that also could be included. So you can think of algebraic size as looking only at the size of the graph, and you can think of the arithmetic size as including everything, also including the bit size of the constants. So somehow algebraic size is the first thing you would want to study. If you start looking at constants, it becomes a harder problem to study. So it's an intermediate thing which is already which has a nice algebraic structure. So you want to study that first. But yeah, if you want to implement everything practically, then also the bit sizes should be small of the constants. That also has to be. But what happens is, when you show that a problem, a polynomial is in VP, a polynomial family is in VP, usually the constants are not too big. Okay, so till now this definition has been is able to achieve whatever we want to achieve.
Saying that is constant, what does it mean?
No. It's constant only means that it is in the base field. It doesn't mean that its bit size is constant. That, so because for every n there is a circuit, you are looking at a circuit, right? So the constants will depend on n. As a they are actually they grow like a function of n. They may grow. They may not be absolute constants.
So why wasn't the depth parameter restriction was there in the definition of VP?
Right. Yeah. So that will have a deep answer later in the course. Yes. So that Valiant did not know, but ultimately he was proven right. So the depth condition is not needed. It can be deduced from the definition of VP with a complicated proof. We will see that proof.
As of now, depth is already bounded by size.
Yeah, so right now, trivially, the depth is just, you can only see it as poly n, but it will be far smaller. So we will see a theorem later in the course where we will show that the depth, you don't need depth more than log n. Okay, so the depth will turn out to be far smaller than what you see a priori in the definition of VP. So that also shows that VP's definition is the most natural one. Okay, and it gels very well with the idea of parallel algorithms instead of sequential algorithm, which is what Turing machine simulates. So this so this is done to be able to implement such circuits efficiently. If one wants. Okay, that's the remark about the definition. You don't need to read the remark, but if you are curious why the degree condition, then this is kind of a vague explanation. Yeah, any other question?
also x raised to 2 raised to n is not in VP.
Yes, so
This kind of
right, so let's take that as an example. So the family x raised to 2 raised to n, and let us look at this sequence of polynomials where effectively the variable is only one. For the nth polynomial is just, it has only one variable, but the degree is actually growing with n. This family is it in VP or not? By definition it is not in VP, right? Because if you just match with the definition, Fn is equal to x to the 2n, x to the 2 raised to n, and so you can actually draw a circuit of size only n, order n, but it will not have the property that degree at every node is poly n, right? The degree ultimately becomes 2 raised to n. So this is an example that looks like an easy example, but it is not in VP. And the reason why you would not want it to be in VP is because if you evaluate it at x equal to 2, then it is giving you the number 2 raised to 2 raised to n, which is too big. Okay, this is not considered an efficiently storable number. So you want to exclude such computations. So though it is computable by order n size circuits.
We have to also specify the underlying field as well, right? Like 2 to the n.
Right. But the degree is too high. The degree is not poly n. Right, so the other point is the class VP will depend on a field, so we have some, implicitly we have some field in mind. So we keep some field in mind. We keep some field F in mind while defining VP. Okay, so for every field there will be a different VP. So ideally we should call it VPF. Okay, but usually we'll know what the field is, so we'll not use VPF. But this is really a definition for VPF.
Field constants cannot be dependent on n, right?
No, the field elements in the field, whatever elements are available. So if you are looking at the field of rationals or the field of complex, then you can use 2 raised to n. 2 raised to n is a constant. Why not? You can actually even use 2 raised to 2 raised to 2 raised to n. You can use arbitrarily large constants because they do not contribute to size or degree. So constants do not contribute. That is another thing to take care of or to take note of. So constants don't contribute, don't count in size. Sorry?
Just to x plus 1 to the n, the constant in the middle grows exponentially.
Right. Yes. Which is fine. Yeah. No. So x plus 1 to the n, the constant grows implicitly. In the circuit, you don't use big constants, but you are also allowed to use big constants. Arbitrarily, big constants can be used because, as I have written the definition, there is no mention of constants being counted in the size or any other resource like degree. Okay, so this is why it's a purely algebraic model. There is no the constants are being ignored. And this is only because we want to create a good theory, so we don't want to. If we start counting also the constants and their bit sizes, then we will be basically doing what people do in Boolean circuits or in Turing machines. Okay, that will become more, I mean, harder to analyze algebraically. So for now, we want to see what we can do algebraically. So the conjectures we make here are in a way stronger, because we are saying that when we say that a circuit doesn't exist, we actually are saying that a circuit using whatever constants you like doesn't exist. Okay, so these non-existence theorems are stronger in this model. Any questions? Okay, so yeah, so you saw a polynomial that is not in VP just because of its, so the proof is, formal proof is via degree argument. Final degree is so large that it can never be computed by VP. So can you think of an interesting polynomial that is in VP? A very complicated polynomial in the definition, but still it is in VP. Right, so we'll study that now. That's a rookie question. So an interesting polynomial family. So we'll skip the word family, but always it will be an infinite family. So an interesting polynomial in VP is the determinant. Right. So what is determinant? So determinant is this polynomial. We'll call it det n. It takes an n by n matrix, let's say big X. So ijth entry of this matrix is X sub ij. So there are n square variables in this matrix, and it is just, this polynomial is a sum of some very special monomials, right, which is go over all the permutations on n. Look at the sign of the permutation, and the monomial is just this. Okay, so the monomial is so the monomial is just of degree n. You are picking those n variables where the second coordinate is a permutation of the first coordinate, so of 1 to n. Okay. So if you think of the matrix, then you are essentially picking variables in the matrix which don't have the same row or the same column. Right. So how many such choices are there? N factorial, right? So n factorial such monomials. So n factorial is around n to the n by 2, right? So as n grows, the number of monomials in this sum grows rapidly. It's more than 2 raised to n. It's a lot of monomials, and we are summing them but with signs, right? So the constants are only plus minus 1 or 0. Okay, so that is the definition of determinant as a polynomial. And right, so this you already know. So given a point, given a specialized matrix, we can compute determinant in, so how fast can you compute determinant given a matrix?
3.7.
Yeah, so I mean at least in polynomial, deterministic polynomial time, right? So you can actually compute it even in smaller than n cube time, subcubic. So there are subcubic algorithms or nearly quadratic algorithms. Okay, but that is not very important. What I want to point out here is that it is in polynomial time. So poly n, despite the definition using n to the n many monomials, right? So which is surprising. So clearly the algorithm, polynomial time algorithm, does something very special. It is not using the definition directly. It is using the properties that the definition entails, right? So what is this algorithm? Right. So this is using Gaussian elimination. So use Gaussian elimination. So over a field, you can use Gaussian elimination to bring the matrix X basically in triangular form, and then once you have a triangular matrix, you know that determinant is just product of the diagonal entries. That is the algorithm. Yeah. So it's basically an incremental algorithm. Okay. Or if you want, it's a recursive algorithm. But you always usually you implement it in an iterative way. Okay, so right, but does that mean determinant is in VP? So this shows that determinant evaluation can be done in P, right? But does this also mean that determinant polynomial is in VP, the infinite family?
Degree of every monomial is not high.
Can't it? Because you have to divide in the family domain.
There are more number of monomials.
Exactly. So Gaussian elimination actually requires division, and we cannot do division. At least by definition, we cannot do it. We can only add or multiply, right? So this doesn't mean this doesn't give the determinant polynomial in VP. So here again I am abusing it. I should actually use the set notation, because when I say determinant, I don't mean a single determinant, I mean all the determinants for every n. So this infinite family, we don't deduce that it is in VP because we have used division above, because the algorithm uses division. So is that the only problem? Well, the algorithm will use not just division, but it will also use if then else, right? It will check whether an entry is 0 or non-zero. It will also permute the rows and column. So all that, how will you do by addition multiplication gates? So almost anything that this algorithm is doing, we cannot directly implement in arithmetic circuits, right? So division, if then else, permutation, etc. So yeah, it may be confusing at first sight, but later on it will become natural. The reason why this algorithm doesn't give you an arithmetic circuit is because to run this algorithm, you need a specific matrix. You need a matrix of constants. You cannot run this algorithm on just a symbolic matrix. You cannot assume n by n or n square formal variables, right? So if you think about the C program that will implement this, that C program will actually assume that you are given field constants, and then it will do arithmetic in that field of constants, not with formal variables. With formal variables, yeah, it will become too expensive just because of repeated division and blow-ups.
Just get back the same polynomial, right? If you work in the function case.
Yes, if you just if you just do it trivially, then you will be incurring a cost of n factorial. There will be no advantage. Right, but if you try to translate this algorithm step by step, then the problems are, well, how do you translate division? How do you translate if then else? How do you translate the permutation? So it's not, these things are not really clear. So the translation is not very smooth between algorithms and circuits. So yeah, this will actually need a full-scale investigation whether determinant is in VP or not. Right? This will be an additional property of determinant if true. It's not trivial. So this is so value computation versus function computation. That is basically the difference. Okay, so when you look at a C program that is computing determinant, that is actually computing value of a determinant at a fixed point, while arithmetic circuit computes the whole function at once. So it gives you the function as a circuit, and then you can do whatever values you want, whatever points you want to fix. So this is much stronger than just Gaussian elimination algorithm that we are asking for. Okay, so yeah, some of you already know that determinant, or you can guess that determinant will be in VP, but we have not shown it yet. Okay, so we'll prove that in the future. Let us move on to the next class.
The circuit size is itself polynomial, so evaluation will also be.
Right. Well, so just by the definition of VP, that is not implied, because what if you are using crazy constants? Such large constants that, so if you are using a constant that has, let's say, 2 raised to n bits, so that arithmetic circuit, you may not be able to just code as a C program, because you will need that much of space to store 2 raised to n bits. But that is not how life works. So whenever we'll show some problem in VP, we'll always get good constants and a good uniform circuit. Okay, so it will also be a practical algorithm. So we have defined VP and we have shown what is there and what is not there. So let us now move to NP. What is the analog of NP? And in general, what is the analog of non-determinism? Right? What is the answer?
Projections, kind of. Because when you take an NDTM, like each path is like a deterministic cube.
Right. So instead of projection, I will simply say sum. Right. So non-determinism is basically, I mean, in the Boolean word, it was whether there exists a certificate. So over all certificates, you want only one. So you are kind of taking OR over exponentially many things. So here in the arithmetic or algebraic word, you will just take a sum. Okay, so do a large sum. Okay, that is vaguely speaking, that will be the analog, arithmetic analog of NP. So how is this implement it, so again Valiant gave this definition. So a polynomial family right, so again Fn is n-variate for all n. This is in VNP if you can write Fn, let's say it has variables x, if you can write it as a large sum over some other polynomial g. Okay, so the sum is over the whole space. This is an exponentially large space. Tn is some polynomial in n, so Tn is not much bigger than n. So G has how many variables? G has n of these x and Tn of the w. So G has n plus t variables. And what do you want? The property that you want on G is that it should be in VP. So Gn should be in VP, and Tn should not be too large, which is obvious.
Size of x bar plus w bar is n.
Size of x, is poly n. Well, Tn is poly n, so everything is, I mean, the arity of G will be poly n.
Because when you say Gn is in VP, that means Gn plus t.
Yeah, sure. That is again obvious. Right. So this, well, so it may, why this definition is natural may not be obvious. We have to look at it for a while, but so to compare it with NP, let us give these things names. So let us call W bar to be witness or certificate. Okay, so W bar is the witness string, and G bar is, or G is, let us call G the verifier. Okay, so we will say that a polynomial family Fn is in VNP if Fn can be written as sum over witnesses with verifier evaluated. Okay, so if you replace this sigma by OR, then you can recover the definition of NP, right, in the Boolean case, because G, you can think of G as the verifier algorithm, which will be polynomial time algorithm, and it is just going over all the possible certificates, and for one of them.
NP is received or this is not received.
Sorry?
So NP is, we just look at some certificate, it is 1. Boolean.
Yeah, so OR of this will be happening in the Boolean word. G will be a efficient verifier. So syntactically, that is the motivation for this definition.
Basically, then every sum is computing some monomial.
Every summoned, the summoned is a polynomial, which is in VNP. It's a complicated thing. It can be determinant, for example.
If a polynomial is self-reducible, right? Something self-reducible, then it is kind of infinite, right? Because you can write it as a projection of it. No, but it has to be in VP also.
Okay, so yeah, if we replace sigma by OR in the Boolean word, we get the definition of NP. So that is the motivation for this definition. Yeah, more than this, there is not much to say that why we are using this. So we are using this solely because of this definition of NP, and so now how do VP and VNP compare? What can you say immediately? Right. So is it true that VP is contained in VNP? Why is that? Right. So if you have a VP family Gn, right, then you can just in the definition just ignore the witness string. So then Fn is equal to Gn, and if Gn is in VP, it's also in VNP. Right. So this is trivial containment. Right, but are there candidates of are there candidate polynomials that you can see immediately in VNP, but you don't believe them in VP? Actually, you currently don't even know whether determinant is in VP, but that later on you will see it's in VP. So determinant is out. So what is the next candidate? Well, you know everything. Okay, so a standard problem in VNP is what is called permanent. Permanent is very close in definition to determinant, but very different in reality. So permanent polynomial again evaluates on an n by n matrix, and it is again a sum over those monomials, as you saw before. But what is the change? There is no sign. So it is again a sum over all the elements of the permutation group on n elements. So again you have n factorial monomials, but there is no sign. So all these monomials appear equally. Right. So why would Gaussian elimination fail on this?
Not be seen as a system of equations.
No, you don't have the swap property. So once you swap it, it's called the
I
negative.
mean, if you take those three properties, which allows you to do Gaussian elimination, you get the determinant as kind of a unique
Right.
polynomial.
Yeah, that is a stronger thing. But this one simple step of adding two rows or adding two columns, that doesn't change determinant, right? But permanent you don't know, or in general it will change. It will mess up the permanent. Okay, so you cannot just add two rows, and this was critical in Gaussian elimination. This is how the rows were reduced, and you got ultimately row echelon or column echelon forms, or ultimately a triangular matrix. So because that property is gone, well, which is actually the equivalent to saying that if two rows are the same, then determinant vanishes, but permanent does not. Okay, so since that property is not there, we don't know we cannot use Gaussian elimination, and then other than Gaussian elimination we have no other algorithms, no ideas. Okay, so this problem is still in all practical ways, this is the hardest problem. Okay, this is even harder than SAT in a way. Okay, so now is this problem in VNP? So we don't expect it to be in VP because practically it's a hard problem. If it is in VP, then I mean something unnatural would happen. We don't expect it to be in VP, but is it in VNP? So let us show that. That permanent is in VNP. Right. So look at the definition again. So this is the this is one monomial. Now, is this monomial function computable in VP? It is obviously computable in VP, right? Because this is just a single multiplication gate. So this is in VP, but so you can use this potentially as a verifier. The definition, in the definition you had a G, so you can use this as a verifier, but the problem is that it is as you look at different summands for different permutations, from the permutation your verifier has to compute this monomial, right, which is not clear how to do. So if you want to put this inside this G, the G that you had in the definition, and G is a polynomial, G has to be a VP polynomial. So can you think of a G that can compute this? Can you connect these two? So that is not clear, because W bar in the definition of VNP is just a string. So you will have to encode your permutation pi as a string, but then from that string, just using polynomial arithmetic, it is not clear how to get to this xi pi I.
So in this case, we can look G as some combination of extra monomials, and they cancel out in some way.
Right. So, well, so first of all, the first observation is that it is not direct. It doesn't follow from the definition. And second is, well, so maybe we should look at a more complicated G. Instead of just this monomial, we have to think of something more complicated, and that is what we will do in the proof. Okay, so let us use the following. So let G be the function or be the polynomial that takes this n by n matrix, symbolic matrix, and a vector and computes a product. So the product will actually be of linear polynomials. Okay, so how many variables does G have? G has n square plus n variables. Right, this is the arity of the polynomial G. It is clearly a polynomial. So, well, if you look at these linear polynomials, it is basically doing a inner product of B vector B with the ith row, right? So you, for a given B, what it is doing, it is just taking a inner product with every row. So there are n inner products, and it is taking a product of those inner products. So that is what G is. well, I'll also need for technical reasons this constant product. So this is the sign part. This is just giving you, so 2bi minus 1 is either minus 1 or plus 1, right? So this is just the sign of what? Depending on how many ones there are in B bar, the weight of B bar, this will be a sign. So this sign times this is the other is the main part, inner products, right? And now, so this is Rg, and on top of this we'll do a big sum on all the B bars. So what do you expect to get out of this when you do the big sum? So the claim is that when you do a big sum, right, on all the vectors, you will exactly get the permanent. Okay, so this is also called Reiser's formula. So what is the proof of this? Or do you already consider this obvious? Yeah, so the proof will be actually looking at these monomial products. So every, so this red part here, this part is producing these monomials in X bar, and what you can show is that the monomials that are where I mean which are not coming from a permutation, those monomials cancel out because of the sign. Well, so there might have been some linear algebra or some physics motivation. I don't know the exact details, but one rule of thumb here is, if you look at this formula, the claim identity in the claim, if you go modulo 2, right? So modulo 2, determinant and permanent are the same, right? This is the only place where you can compute permanent, because permanent is the same as determinant, and the determinant you can compute. So so modulo 2, there are no signs, and then the sum, big sum is giving you determinant, and maybe maybe that is another reason to look at this sum. It is able to cancel out all these monomials which are which don't correspond to permutations. Okay, so once you do that, then you might try to generalize it to other characteristics.
It will be determinant of how many variables? N square plus n.
It will be det n. Modulo 2, permanent n is the same as det n. Okay, so let us quickly go through this proof. So we can rewrite left hand side as right. So since B bar is a 0 1 vector, let us go in terms of subsets. Okay, so let us write it as subsets of 1 to n, and the product is over xij's, j in T, and I is 1 to n, and with a sign. So the sign you can see is -1 to the n minus the size of the subset. Is this believable? Right, this is just translating inner product of a 0 1 vector with a row, with the ith row. So when you do the inner product, you are just selecting some elements of the row and adding them. So that is this main part, sigma xij for j in T, and then you are going over all the rows. So that's the product I equal to 1 to n, and with a sign, and then you are taking the big sum over all the subsets, right? So now in this, now since this is straddling over all the n rows, so it is basically multiplying the variables that appear in distinct rows, right? So it is supported on monomials like x1 I1 dot dot xn in. So from the first row you pick I1th variable, second row I2th variable, dot dot nth row inth variable, and then you multiply them, right? That is, these are the kind of monomials this product will produce. So here, say this I1 repeats R times. So the point is, we want to analyze the situation when this monomial doesn't correspond to a permutation, which means that I1 to In is not, they are not distinct. There is some overlap happening. So suppose I1 is repeating more than two or more times, right? So when I1 repeats, we want to show that this particular monomial will get ultimately cancelled in the big sum. Okay, so why is that? So in how many t's will this monomial be produced? 2 raised to r minus 1, right? So so I1, since it is repeating r times, the number of t's which will contribute this is exactly 2 raised to r minus 1, the number of subsets. So the monomial, let's call it M. So the monomial M associates or can be associated to 2 raised to r minus 1 many subsets T. Okay. So well, so whenever this monomial is contributed, there is a sign attached. So let us look at the sum of the signs. So which sign, what is that? Well, it's basically over all the subsets of r minus 1 to the n minus size of S, or even simpler, size of S. Is this clear? So why are you getting r minus 1? Well, so r minus 1 appears because you have to pick at least something, right? So
Would it be like, I mean, you have to, when you pick those, you have to pick I1 R times.
so 1 comma I1.
So you have to pick, so the J's vary, J belongs to T, so you have to pick I1 R times.
No, so let us say x1 I1 appears, and then in the remaining there are r minus 1 more I1s. Okay.
But then that leaves free n minus, I mean, if you from the set 1 to n,
Mm-hmm.
if you want to create a subset that has r I1s, so So you have to, so like you have to have R ions and then you have the rest free, right? So it's like n minus R.
Actually,
And then that varies 2 to the n minus R.
well, so this monomial, in how many ways is it being produced? This is what you are looking at. So the number of ways it is being produced is 2 raised to R minus 1, and the sign is exactly this. And what is the sum of this? What is this sum? Well, this is just 1 minus 1 to the R minus 1. Well, sorry. This is, it's basically just, yeah, just the product of 1 minus 1s. So this is 0. Okay. You basically you can factorize this sum as a product of 1 minus 1s. Right. So monomials. So the thing we assumed is that R is at least 2. Okay. If R is 1, then this argument will not give you anything. So the only monomials that survive are those where nothing is repeating. So I1 to In is actually distinct. So at least the support is correct as we wanted. Next thing you can see is, so what about those other monomials? So this finishes our proof. Well, not really finishes, but you have to make another observation. So for permutations, product of xi pi I survives. In LHS, and it survives with the sign. Yeah, why is it plus 1? Well, it is plus 1 because all these
T was
all the BIs are 1, right?
number of ones in T one.
Right. So it survives in LHS with the sign 1. Okay, so the sum of these monomials is all that remains, and that by definition is called permanent. Okay, so that finishes the proof. Right, so this is called Reiser's formula. It is important because if you try to compute permanent at some matrix, how much time will it take? N by n matrix? More than n factorial, right? So something like n to the n. On the other hand, if you use Reiser's formula, so in Reiser's formula you are just multiplying simple things, just linear combinations is what you are multiplying. And how many times? 2 raised to n. So this will give you a 2 raised to n algorithm, right? So in practical applications where you care for this difference, you would use this because this is 2 raised to n, the other thing, the original thing is n raised to n, okay, which for large n could be significant difference. So this is the best algorithm known to compute permanent in generality. Okay, so for general permanents, this is the best algorithm, and it is quite non-trivial because in the definition you had far more monomials. So somehow that has been compressed. Now the question that remains, which is open, is can you do better? Well, anyways, so we are digressing now. So this our goal was to prove that permanent is in VNP. So that also we have achieved because this G is now your verifier, right? So once you have proved this claim, you should see G as the verifier circuit. Well, why is it in VP? Because it is just a simple product. You just compute these inner products by addition gates and then you multiply by a single multiplication gate. So it is clearly just a depth 2 arithmetic circuit. So that's your verifier and B bar is your witness. So this identity also shows that permanent is in VNP. Okay, you just need to compute this big sum over VP. Right, and it also gives you an algorithm, and you can see that here the constants are very small. So this always happens that when we give a VP circuit or this kind of a VNP expression, the constants are never too large. Okay, so although in the definition we are allowing arbitrary constants, in actual proofs they are always small. So you can also use this as an algorithm. Okay, so I think I'll then stop. Any questions? So next time then we will look at determinant more carefully. Okay, once VP, VNP are defined and we have this candidate polynomials, we'll prove more.